This is MCET 450 Advanced Mechanics, and in this video we're going to review the concepts of centroidal moment of inertia. Take a look at this sketch that's been created here of a three-dimensional beam. This one happens to be rectangular or cubic in shape. Want to pay attention to the various facets of this beam. It's attached back here at a wall. It's free at this end, therefore it's a cantilever beam. But these principles would apply to any other type of supported beam, such as a simply supported or fixed end beam. So let's take a look at the key attributes of this object. We have the length of the object from the wall, one end to the other, and then we have the cross section of the object. That's at the very end here, where we define the base and the height. This center line here, from this end to this end, and obviously imagine it coming through dead center, that is considered the longitudinal axis. Depending how a force is applied in relation to the longitudinal axis, it will result in different types of movement and loading. So for instance, if we have a load applied in such a way that it wants to pitch the axis upward or downward, so it actually physically wants to bend the longitudinal axis one way or the other, we call that a bending moment. And the resistance to a bending moment is the second area moment of inertia. However, if we have a load that wants to twist the object about its longitudinal axis, well, then that is known as a torsional load application as opposed to a moment application. Now, it can be confusing because moments and torque or torsion have the same units. They're going to be force times distance. And we'll talk more about that in detail. But the key thing I want you to pick up here is that what is happening the centroidal axis, or the longitudinal axis of the object that runs along the length through the center. If we're trying to physically bend the axis, then the resistance to that bending is called the second area moment of inertia. If we're trying to twist about that axis, the resistance to that twisting is called the polar moment of inertia. And both of these inertias, the second area moment of inertia and the polar moment of inertia, are functions of the cross section of the object. Now in this case I drew a rectangular object, but if it was a cylindrical object, the same principles would apply. So sometimes where students get confused is they want to incorporate a length calculation into the moment of inertia calculations, but that is erroneous. That is not correct to do. So you always want to make sure that you're basing your moment of inertia calculations on the cross-sectional area, and that cross-section is in relation to the longitudinal axis of the object. Now let's take a look at some basic area and inertia calculations for different types of objects. So I've extrapolated the cross-section. Again, just happen to draw a square cross-section here. A square is of course a form of a rectangle, so rectangles and square cross-sections follow the same set of formulas. On a square, the base and the height happen to be equal. On a rectangle, they are not, but the formulas are exactly the same. So down here I've extrapolated a rectangular cross-section. Now this cross-section would have a base dimension down here and a height dimension over here. Got to keep this in mind. Which one's the base, which one is the height? In a square it doesn't matter. In a rectangle it does. And the way this gets oriented is based on where a load would be applied. So if we're applying a load from the top, then this is our base and height. If we're applying a load from the side, then they switch. And we'll talk more about that in detail as we get into beam bending. But for now, just understand in this orientation, this is the base and this is the height. So we'll first just talk about the basic sectional area, the cross-sectional area. That's a pretty simple calculation. You probably learned it in elementary or middle school. And it's the base dimension times the height dimension. So if this is measured in meters and that's measured in meters, you're effectively multiplying meters times meters, and that gives you units of meters squared. Area moment of inertia is different, however. So if we're going to find the second area moment of inertia, and we can take the moment of inertia about any axis we choose. However, for almost all of our stress and strength of material calculations, we are going to take the moment of inertia about the centroid of the object. That's the same as the center of gravity in most cases. So in a rectangular object like this one, it's going to be halfway up the height and halfway over from the base. So right in the middle, that's your central. And that's where you're going to find your second area and your polar moments of inertia. Notice here's the two equations for second area moment of inertia. We use the variable I, and polar moment of inertia, we use the variable J. And they both have subscripts C because it means they're about the centroid. If it was about the x-axis, the subscript would be an x. If it was about the y-axis, the subscript would be a y. So the formula for the second area moment of inertia of a rectangular cross-section, remember it's the cross-section, we're not using the length in any of these calculations, is the base times the height, but in this case the height is cubed. Remember your order of operations when you do this, it would be exponents then multiply. So it's the height cubed times the base. That's the order of operations. You don't multiply and then cube. That is not what this means algebraically. So it's the height cubed times the base divided by 12. That will give you the second area moment of inertia about the centroid, and that is the resistance the object has toward being bent along the longitudinal axis. So physically bending the axis of this object. The polar moment of inertia, J sub C, is again based on the base and the height, but it's a little bit more involved. It's the base of the object times the height of the object times this quantity, which is base squared plus height squared. So you've got the base squared plus the height squared. You sum those, multiply them by the base times the height, and divide by 12. And that is your polar moment of inertia. And that is the object's resistance toward being twisted, or rather the object's resistance against being twisted, about the centroidal axis. So that's where you use polar moment of inertia. Now we'll look at a circular or cylindrical object. If the object is cylindrical, then obviously the cross-section is circular, right? And much in the same way as a rectangular object, the circular object has its centroid right at the center. So basically the radius to here gets you to the center, right? And what I find in different textbooks is that you will have areas and moments of inertia either based on the radii or based on the diameters of the cylinder. I find it easier to work with diameters because normally that's what we're physically measuring and that's how we're dimensioning that, but working with the radius isn't that much more difficult. So the ones I show you here are based on diameter. Those are the ones I prefer to use. So this cross-sectional area, and again, notice we're not doing anything with the length. Nothing with the length. The cross-sectional area is based solely on the diameter as far as a measurement. It's the diameter squared times pi over 4. Again, we're not multiplying then squaring because that's not the order of operations. We square the diameter, then multiply by pi, and then divide by 4. That's the area. And of course, again, if we're in SI units of meters, base units are meters, you're going to end up with units of meters squared. Now, we didn't talk about this, but what would we end up with for the units on area moments of inertia? Well, think about what we're doing here. It's easy to see on this one. We have a diameter, which would be in, let's say, meters, and it's to the 4th. So, for area moments of inertia, our units are meters to the 4th, or in the case of inches, it's inches to the 4th. Now, back up on this one, it's still the same. You got h cubed, right? So that'd be meters cubed times another measurement in meters. So it still gets you to meters to the 4th. A good way to check that you're getting the right answer is that you got the right units. And what you don't want to do is confuse area moments of inertia with mass moments of inertia. That's what we use in dynamics. Those will have units of mass times area. So like kilogram meters squared would be for mass moment of inertia. If you're looking up a formula to do statics and you're getting units of kilograms in area or something of that nature, then you know you've got the wrong set of formulas. You're always going to have the linear units to the 4th if you're looking up area moments of inertia. So the second area moment of inertia, about the centroid of a cylindrical object or circular cross-section, is pi times d to the 4th over 64. Again, pay attention to the order of operations. You raise the diameter of the 4th first, then multiply by pi, then divide by 64. It's very similar in the case of the polar moment of inertia. It's pi d to the 4th over 32. Effectively, for a cylindrical object only, the polar moment of inertia is double the second area moment of inertia. So let's practice this a couple times using the different formulas. So down here we've got a sample problem. It deals with a rectangle. The base is 2 inches and the height is 4 inches. And what we want to do is find the area, the second area moment of inertia, and the polar moment of inertia. So let's set this up. So the area would be base times height. And we know that the base is 2 and the height is 4. And those are, of course, inches. So 2 times 4 is 8. So that's 8 inches squared, right? Because we multiplied inches by inches. The area moment of inertia, second area moment of inertia to be precise, I sub c equals base height cubed over 12. So that would be the base of 2 times the height of 4 cubed divided by 12. Those are inches, of course. So 4 times 4 is 16. 16 times 4 is 64. That's times 2 and divided by 12. This is effectively 128 divided by 12. So that's 10.67 inches to the 4th. Now let's set up the polar moment of inertia. I'm going to flip over because we're running out of space here. I'm going to write it on the back side here. So our formula for the polar moment of inertia, J sub c, this is for a rectangle, is base times height times the base squared plus the height squared divided by 12. So I didn't misremember it. No, that's correct. And so remember, our base is 2 and our height is 4. So this equals 2 times 4 times 2 squared plus 4 squared divided by 12. Of course, 2 times 4 is 8. At that point, we end up with inches squared, right? Because we just multiplied inch by inch. And we're going to multiply that by 2 squared is 4. That's 4 inches squared. Plus 4 squared is 16. And that's still inches squared. So now you have inches squared times inches squared. That's going to get you your inches to the fourth. So 4 plus 16 is 20, right? Let's write this out. Divided by 12. So yeah, you have 8 times 20 divided by 12. So that's effectively 160 divided by 12. That's 13.3 inches to the fourth. So we did all 3 of the different calculations for the rectangle. Here's the circle, and we're told it has a diameter of 0.5 meters. What are the area, second area moment of inertia, and polar moment of inertia for the circle? Why don't you pause the video here and use these equations and see what you come up with for an answer, and then check back and see if your answers agree with mine. I'll give you a moment to pause the video. Okay, hopefully you've come up with some answers. So we'll start with the area. Move the page up a little bit so you can see what I'm writing. So the area of a circle is pi d squared over 4. So that would be pi times 0.5 meters squared over 4. Can't do that one in my head, so we'll do it in the calculator. That comes up with 0.196. We said meters, so we're meters squared. Now let's look at the second area moment of inertia. So I sub c equals pi d to the fourth over 64. That's going to equal pi times 0.5 raised to the fourth divided by 64. And that is equal to 0.00307 meters to the fourth. And lastly, we have the polar moment of inertia, which is very similar. You can effectively could double this if you want to, but we'll just write it out. J sub c equals pi. We'll fill in the diameter right there for space, times 0.5 to the fourth divided by 32. So that one equal to 0.0061 meters to the fourth. See, that's effectively doubled with some accounting for rounding. So it will be very important in this course that you understand how to find the different moments of inertia and areas, and understand how they apply to the object that you're looking at and analyzing. That's it for this video. Thank you for watching.